We've already seen that the allowed values for the spin quantum number are positive 1/2 and negative 1/2. So an electron could have spin up or an electron could have spin down. And remember, spin is in quotation marks because we can't really visualize an electron spinning on its axis. That's not really what it's doing. And so we just call it the spin quantum number. And so let's say we have two electrons, and each of our electrons has spin up. So let me go ahead and draw that situation here. So we have two electrons with spin up. Well, an electron is a moving charge, right? Moving charges produce magnetic fields. And so an electron is really just a tiny magnet. And when you have two electrons with parallel spins, the magnetic fields of those electrons add together. So we call this situation paramagnetic. So this situation here is paramagnetic. The magnetic fields of the electrons add together. If you have a situation where you have one electron with spin up and one electron with spin down, the magnetic fields of those electrons cancel each other out. And so we call this situation diamagnetic. And let's get some better definitions for paramagnetic and diamagnetic. So let's move down to here and let's look at the definition for paramagnetic. So something that's paramagnetic has one or more unpaired electrons. So we talked about an example where we had two unpaired electrons. But of course, you could just have one unpaired electron, right? So that's like a tiny magnet with its own magnetic field. And so something that's paramagnetic is pulled into an external magnetic field. It's attracted to an external magnetic field. And we can figure out if a sample is paramagnetic or not by using this special balance that I have. I have this picture of this balance drawn down here. So let's say that our paramagnetic sample is in here, so right there in magenta. And we haven't turned on the magnet yet. So here we have a magnet. There's a north pole and a south pole. So before we turn the magnet on, let's just say that our paramagnetic sample is balanced by some balancing weight over here on the right side. Right? So there's a pivot point right here, but we have everything balanced perfectly. Right, so let's now turn the magnet on. So we turn the magnet on, and the magnetic field lines go from north pole to the south pole, like that. And if we have a paramagnetic sample, right, with one or more unpaired electrons, our paramagnetic sample is pulled into this external magnetic field that we've just turned on. And so this is pulled down, right? So this whole part is pulled down. And so let me go ahead and redraw it here. So this would be pulled down into the magnetic field. And so our paramagnetic sample, right, is pulled into the magnetic field. All right, what does that do to our balance? Well, of course, that's going to pull this side down, right? And so that's going to pull, and our balance is going to rotate about this axis, right? And so this part's going to go up, right? So just simple physics. And so this weight's going to go up. And so it's like our paramagnetic sample has gained weight. And of course, it hasn't gained weight. It's just experiencing a force. There's a magnetic force because it is a paramagnetic substance. And so this balance allows us to figure out if something is paramagnetic or not. Let's look at the definition for diamagnetic. So for diamagnetic, all electrons are paired. Right? So if we have spin up, we have spin down, and so the magnetic fields cancel. And so a diamagnetic sample would not be attracted to an external magnetic field. Actually, it produces its own magnetic field in the opposite direction, so it's actually weakly repelled by an external magnetic field. So we have these two definitions, paramagnetic and diamagnetic, and we can figure out if atoms or ions are paramagnetic or diamagnetic by writing electron configurations. So let's look at a shortened version of the periodic table, and let's look at some elements, and let's figure out whether those elements are para or diamagnetic. Let's start with helium. So helium right here, we need to write the electron configuration for helium. So this would be 1s1, and then we get 1s2. So I'm assuming you already know how to write your electron configuration. So we have 1s2, which means we have two electrons in a 1s orbital. So here's our 1s orbital. We have two electrons, and they must be spin paired. Right? So the electrons are completely paired, and that means that helium is diamagnetic. So helium is diamagnetic. So helium atoms, I should say. Let's do carbon next. So let's find carbon. Let me change colors here. So here's carbon on the periodic table. If I wanted to write an electron configuration for carbon, well, it would be 1s2. Right, so I'll start 1s2, and then we have 2s2. So 2s2, and then we have we're in the 2p1 and then 2p2. So 1s2, 2s2, 2p2 is the electron configuration for carbon if we write in orbital notation. Right? So we would have our 1s orbital here, and our 2s orbital here, and then we have 3 2p orbitals like that. So put in your electrons. We have 6 electrons, right? So 2 in the 1s orbital, so we put those in. 2 in the 2s orbital, we put those in. And remember Hund's rule, right? We have 2 electrons in the p orbitals, but we don't pair those spins, right? We don't pair those spins. And so we have unpaired electrons, right? So we have unpaired electrons here for carbon when we draw out the orbital notation. And unpaired electrons means that carbon is paramagnetic. So carbon is paramagnetic, carbon atoms anyway. All right, let's do sodium next. So let's find sodium down here. So here's sodium. We need to write the electron configuration. All right, so that would be 1s2. So let's write 1s2 in here. 2s2. Then we have 2p6. So 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So 2p6. That takes us to the 3s orbital, right? And so 1 electron in the 3s orbital, so 3s1. So 1s2, 2s2, 2p6, 3s1 is the electron configuration for sodium. If we did that on our on an orbital notation, right, we would have 1s orbital, right? So we have 2 electrons in the 1s orbital. 2s orbital, we have 2 electrons in the 2s orbital. 2p orbitals. Right, we have 1, 2, 3, 4, 5, 6, and then we have 3s1, right? So we have the 3s orbital right here, 1 electron in the 3s orbital. Well, notice, right, 1 unpaired electron. An unpaired electron means paramagnetic. So sodium is paramagnetic, sodium atom anyway. All right, finally let's do sodium ion, so Na+. So the sodium atom has equal numbers of protons and electrons, but the sodium ion, we've lost one of those electrons, right? So we're going to lose this outer electron here, right? So the sodium ion has this for an electron configuration, 1s2, 2s2, 2p6. And so we lose this one electron. Notice for the ion, now we have all paired electrons, right? So everything here is paired. And if you have all paired electrons, we're talking about diamagnetic. So while the sodium atom is paramagnetic, the sodium, I misspelled that there, the sodium ion is diamagnetic. And so it's just about writing your electron configurations and thinking about the definitions for paramagnetic and diamagnetic.